Hi everybody. The last time we met we talked about the law of conservation of momentum, and today we're going to be looking at a practical application of the law of conservation of momentum, which is dealing with collisions between objects, or what happens if an object explodes. There are several different types of collisions that we're going to look at. However, the one thing that will always tie all of our problems involving both collisions and explosions together is that as long as there's nothing external to the system acting on our objects, which is usually going to be the case, for any kind of collision or explosion, the total momentum will be conserved in all cases. So the first type of collision we're going to look at is what we call an elastic collision. And an elastic collision is sort of exactly what it sounds like. We think of elastic as being something sort of stretchy or bouncy, and an elastic collision is where the objects are going to bounce off of each other perfectly. Anytime you have an elastic collision, you're going to have the same number of objects both before and after the collision. Nothing will stick together and nothing will break apart. The second thing that will always be true in an elastic collision, and what really defines it as an elastic collision, is that the total amount of kinetic energy is going to be conserved. And the reason this is special is because this means that none of the energy is being converted into heat, which is what happens in a lot of cases. The example that we saw in class of an elastic collision was the cars with the magnets that repelled each other. Another situation in real life that you might have seen where the objects behave at least pretty close to being elastic is pool or billiard balls colliding into each other. Usually elastic collisions are going to be between really rigid objects that can't bend or deform or do other things that would cause a lot of random motion energy or heat to be generated. If a collision is not elastic, the other thing it can be is inelastic. And what makes a collision inelastic is simply that it's not elastic. If elastic collisions require the total energy to be conserved, in an inelastic collision we're going to have some kinetic energy lost. Of course, we know from the law of conservation of energy that the energy can't truly be lost. What we mean is that it's no longer useful mechanical energy. It's been converted into heat. Inelastic collisions are far more common. They're what's going to happen pretty much any time that the objects deform in any way when they're colliding into each other. However, if the objects deform a lot, in fact, if they deform so much that they stick together, we can have what we call a completely inelastic collision or a perfectly inelastic collision, which is sort of like the end case of the inelastic collisions. It's where we would have the absolute most possible kinetic energy lost. And again, what makes it completely inelastic is that the objects stick together. So you're generally going to start with like 2 objects and you're going to end with only 1 object. And if they stick together, if they deform so much that they stick together, this is going to result in the maximum possible loss of kinetic energy. The last situation that I want to talk about are what we call explosions. And an explosion isn't really a collision, it's sort of the opposite of a collision. Specifically, it's the opposite of a completely inelastic collision. An explosion is any time where you have one object at the beginning and then something happens where it breaks into more than one piece. And you wind up with multiple objects at the end. As you might imagine, if it's the opposite of a completely inelastic collision, instead of losing kinetic energy, we're going to gain kinetic energy. The example that we saw of this in class was when we had the 2 carts with the spring-loaded plunger armed in between them, and they started off at rest, and then when we hit the button, they exploded apart. And so there was some stored elastic potential energy inside the spring before we hit the button, and then that was converted into kinetic energy inside the carts. And so at the end, they ended with more kinetic energy than they had at the beginning. So we're going to look at some problem solving of how we mathematically deal with both collisions and explosions, and we're going to look at situations in both 1 and 2 dimensions. These are going to be out of our packet, which has been posted on Schoology. We're going to do some of the problems together as samples, and then some of them are going to be left